I've posted videos before about my model railway point controller, but this video is different. Instead of explaining how it works, it's going to talk about some of the problems I faced when implementing this, and lessons learned, explaining some of the decisions I made and some of the things that went wrong, and things I could have done differently. I didn't actually have flames, but I did generate lots of blue smoke in the process, and I've added a broken Raspberry Pi Pico to my Raspberry Pi graveyard. So here are some of my mistakes, so you don't have to make the same ones. So here are some of the things I'm going to cover. First, a quick introduction to the project and confirmation that it's actually working now. I'll talk about some of my first design ideas and how I killed a point motor solenoid with blue smoke. I'll talk about some of the design decisions and compromises I made, some of the problems I encountered with the hardware and the software, and I'll mention some about how I could have done this differently, possibly a change in direction for the future of the project, followed by some final thoughts and a summary about the whole experience. I've already covered the details of the project in other videos, so I'm only going to provide a quick summary and update. See the link in the description for more details. So this started out as a way to control the points on my son's model railway layout. It uses a Raspberry Pi Pico as both a physical interface using toggle switches and a GUI application running on a Raspberry Pi connected over Wi-Fi. Since then I've created my own demonstration board, which is what you can see here. It has 5 points which are controlled by the point controller. The controller PCB with the Raspberry Pi Pico is mounted under the board. There's a separate PCB in the console. There's also a Raspberry Pi and a touchscreen. This is designed to work with solenoid-based point motors. So this shows how a solenoid point motor works. There are 2 coils. Power is applied to one of the coils at a time to switch the point from one side to the other. As these are electromagnetic devices, they use a relatively high current when turned on, and the coil should then be powered off once it's switched over. My first problem was several years ago, when I first started to automate an earlier model railway. And this was before the Raspberry Pi, and I used an Arduino to control the points. I had a bug in my code which resulted in the solenoid being stuck switched on. This resulted in the solenoid overheating, resulting in blue smoke and a burnt out point motor. These motors typically cost around £6 to £15, so not very expensive, but you won't want to break them too often. The solution was to add a capacitor discharge unit. I've covered this in another video, but it overcomes many of the issues with solenoids by storing the charge into large capacitors, which can provide a quick pulse of energy to the solenoids. The capacitors don't start charging up until after the solenoid has then been switched off, reducing the risk of any blue smoke. I created the controller to support a maximum of 4 points. This was based on the number of points on the initial layout, but it's also a convenient number based on the ports on the MCP23008 GPIO expander. Each GPIO expander could support 2 switches and 4 LEDs, so it could be used for 2 points. Using 2 of those allowed for 4 points, which was quite convenient. I could have used more boards, and I did think of extra expansion boards, but the other option is just to add multiple point controllers. They could even be connected together. The problem was that for my demonstration layout I had 5 points, and it really wasn't worth creating a whole new set of PCBs just for 1 additional point. A solution to this is that 2 of the points I used to form a crossover between 2 tracks, and it only makes sense to switch these together. Essentially, they're either on their own track or connected to the crossover section. So it made sense to operate these as a pair. They're connected in parallel and controlled by the same switch. I've added an extra pair of LEDs in series, which makes it clear which line is activated on the control panel. The next thing is that I was originally intending this to be powered with a 12-volt power supply, which is also how I've labelled the PCB. When I was first designing and testing this, I used a Gaugemaster point motor, such as the one shown. But on the actual layouts, I use a combination of different point motors. When I tried with other point motors, they struggled. It appears that the Gaugemaster motor has a good range of voltages that it supports, whereas some others are designed for 16 volts. That's quite a common voltage for model railway accessories. I tried with a 15-volt power supply, which works with some but not all the point motors. You consider the voltage drop in the diode, the MOSFET in the CDU, and the power MOSFET used to switch the motor. Then there's a bit of voltage drop in each of these, and in the end I went with the 19-volt power supply. Unfortunately, they're quite common, especially with older laptop power supplies, which I had some spare ones. When you take into consideration those voltage drops, then starting with 19 volts, the output is actually just a little bit over the 16 volts anyway, so that actually worked out quite well. The next thing I found really infuriating was that Peco and Hornby use the same colour wire for their motors, which is red, green and black, but use the colours to mean different things. I'd used the Hornby motor before, which is like the one shown on the left, and I wired these both up based on that. I couldn't understand why one of the motors wasn't working, and it turned out it was the Peco. Despite having the same colour wires, they needed to be wired completely differently. I also found the point motors work better when you match the manufacturer of the point motor with the track. I have a mix of track and point controllers, and in most cases I was able to install them, but I had a problem with the Peco motor, which was just sticking occasionally when I used it with the Hornby point. I created a shim to raise the Peco point controller up slightly. Fortunately, it was easy enough to create in FreeCAD. You can just see it over here. So I created the design in FreeCAD and laser cut it in 1mm balsa. I'm not sure whether this next one counts as a bug as such, but it was unintentional. It was the choice of footprint for the 2N7000 MOSFETs, and these are small TO92 devices. I designed the PCB for hand soldering, and I chose the standard TO92 inline footprint. When I got the PCBs, I realised the pads were incredibly close together, making manually soldering very difficult. The PCB shown is on the left, and the actual PCB on the right, but bear in mind the view on the right is from the bottom up. So let me just flip the image of the PCB, and now that makes a bit more sense. You can see how the position of the MOSFETs line up with each other and the soldering point on the actual PCB. So I managed to solder the bottom one fine, but my first attempt at the top one, as you can see, is a little not so tidy, and there's actually a bridge that's between two of the connections, so that wouldn't work. Now I should be able to fix this with a bit of desoldering braid, and when I moved on to the others, this was my first attempt, I sort of got a technique using a fine soldering iron, a bit of extra patience, and I've been able to solder all the others fine since. But realised afterwards, if I'd selected the TO92 inline wide footprint instead, that would have made that soldering a bit easier. It's not the hardest soldering I've done. In the past, I've done some soldering of an LCD display which had a very fine pitch, and that was quite difficult. But this is still not as easy as it could be, and for the sake of selecting a different footprint in the PCB design, it would have been slightly easier. Another problem was that of broken wires. I decided to hardwire directly to the PCB, but I used Cat6 networking cable. Just snip the end off and then use the wire from that. Unfortunately, when I was testing it, there's quite a lot of movement on the wire, and it broke where it connected to the PCB. With hindsight, I wish that I'd used the pluggable terminal connectors that I'd used on the main PCB. That would have made it easier to connect and disconnect the wires, and would have made it much easier to fix one of the broken wires. So that's a lesson learned for future. The next problem was a bit strange. It was related to the MCP23008 GPIO expander. Normally these integrated circuits are quite robust, but for some reason one of these failed. The difficulty was in knowing that these were the problem. Where do you start looking? In this case, it wasn't too difficult, as it resulted in a short circuit between the I2C ports and ground. So a quick test with a multimeter, I was able to see there was something wrong with one of the ICs. Fortunately, I'd used IC sockets for the chips, so they could just be swapped in and out without too much difficulty. Swapping the GPIO expander removed that short circuit, but it still wasn't working. I wasn't able to communicate properly on the I2C bus. So where could the problem be? In this case, it turned out to be the Raspberry Pi Pico and the same I2C pins. This shows a typical waveform of an I2C communication. This is taken on my oscilloscope. And the top line in yellow is the data line and the bottom is the clock. It's a little bit noisy, it's not a particularly sharp signal, but it's quite clear to see where one should be a high voltage and one's a low voltage. And there's a significant difference between that. I think some of the noise was probably because this is testing on a breadboard and some of the wires were probably picking up a bit of noise. When I tried with that particular Peco, then the output was basically pulled low all the time. So it just wasn't getting a signal out of the Peco. My first thought was if the GPIO expander that had been faulty had damaged the Peco. But because of the voltage level shifters that I used, it shouldn't have been possible for a problem on the GPIO side, which is shown here by the 5 volt side, to propagate to the Peco, which is the left hand side, the 3.3 volt side. However, I've used this Peco in multiple other projects. It's more likely that I've somehow shorted the pins out or accidentally connected them to 5 volts on a previous project. So it's another Peco's not working, so it's gone to the Raspberry Pi graveyard, but at least it's quite inexpensive, and I'd got another Peco that I could swap out without any problems. Although I still had a few more problems to go. It wasn't just the physical pins I had to deal with, but also a problem with the I2C signal, in particular with the hardware-based I2C used by default with MicroPython. This is the third instance of the point controller, and the first two worked fine. One had the switch PCB in the same enclosure as the mainboard. The other had it in a separate location, but it was still fairly close. This time I had quite a longer wire between the two PCBs, which was the I2C bus. And it also went through a connector. And whilst this should be well within the design specifications of I2C, when I tried it, it was able to detect the chips okay, and you could see that they were responding, but then I'd get a timeout whenever I tried to change the status or read the status of any of the pins. Fortunately, the fix was fairly easy, just switching to software-based I2C, which I understand has probably a better time intolerance, and that might be why it works better. But it took me a lot of time trying to figure out where it could be before I got to that point. So just a little something to be aware of. The final bug, this was embarrassing. I'd fixed it once before, and I brought the bug back in this version. So when I pressed the buttons through the web interface, it would only throw the point in one direction. It was a simple bug in the JavaScript where it was sending the same signal regardless of which button was pressed, the result of a simple copy and paste error. But as I said, I'd fixed this before, and I happened to have copied the old JavaScript file onto this Peco. I normally use GitHub for source control, and indeed I have for this project, but this was before I'd actually put it into GitHub, and I'd got 2 copies of the file on my computer, and I'd, for some reason, copied the wrong one. Another lesson learned. Finally, what would I, or perhaps will I, do differently? The obvious thing is that I could perhaps fix some of those remaining issues that I've already mentioned, in particular the space in the footprint on the 2N7000 MOSFETs, which it's quite easy to swap on the PCB, and I'd do that if I was doing another PCB run. And also using different connectors for the I2C connection. The other thing though is that since starting this project, I joined MERG, the Model Electronics Railway Group, and they're well known for their use of the layout control bus, which is quite popular amongst the group. typically CBus, which is based on CAN bus. But also currently under discussion is VLCB, which is based on CAN bus as well and interchangeable. I'm therefore considering doing a different design using that instead. For anyone not going down the layout control bus method, then I2C is still a good solution. But as I'm looking at implementing a layout control bus anyway, it makes sense to consider that as an option and just connect to that rather than having a separate I2C bus. And some final thoughts. Just like to say this has all been part of a learning curve, and that's common whenever trying to do something new in a project, and sometimes even when you're doing something you've done before. While some of these have been a bit of a distraction from getting it working, it's actually quite satisfying when fixing the issues and the feeling that you get when you've achieved something. We all make mistakes, all learn new things as we go along, and the key is not to be afraid of making those mistakes, otherwise you may never achieve anything. Thanks for watching. If you've not subscribed yet, please do so, and give this video a thumbs up if any of it was useful to you. As always, there's more information on my website, or see some of my other videos related to these projects. I look forward to seeing you in a future video.